Project ER 2727 examines what happens to energetic compounds in the field when they're exposed to sunlight, rainfall, and varying temperatures. Most likely route for insensitive and traditional munitions deposition on military training ranges is as residues of low-order detonations. The residues are particles that include several energetic components with different properties. Project examined traditional formulations like composition B and C4 with TNT and RDX, as well as recently developed insensitive munitions formulations, IMX 101 and 104, that include nitroguanidine NQ, dinitroanisole D9, and nitrotrazolone NTO. Their dissolution and phototransformation was measured across 3 locations with different climatic conditions. The project complemented these studies with controlled lab experiments. These measure transformation rates of energetic compounds as a function of amount and wavelengths of incident light, whether compounds were in solution or in solid form, in dry or moist conditions, and if they were adsorbed to mineral surfaces. Project also identified products of phototransformation. In addition, ER 2727 looked at adsorption of released compounds to soil and its reactive components to examine mechanisms of factors influencing adsorption. Transport in soils of energetic mixtures resulting from outdoor dissolution and phototransformation was also studied. The dissolution of energetic compounds followed individual solubilities of the formulation components. NTO dissolved first, followed by NQ, D9, TNT, and RDX. In 2 years, up to 96% of NTO dissolved from IMX 101 particles and only about 5% of D9. Dissolution rates increased with decrease in particle size, and this effect could be quantified using calculated surface area of the particles. Dissolution also increased with the amount of precipitation, but relationship was non-linear. Particles in wetter conditions dissolved faster, possibly due to more frequent rainfall or greater relative humidity between rains. D9, NTO, and NQ were shown to transform when exposed to UV light. D9 transformed to mesoxynitrophenols, mesoxynitroanilines, and dinitrophenol, NTO to uracil, nitrate, nitrite, and ammonium, and NQ to guanidine, cyanoguanidine, nitrate, nitrite, and ammonium. Many of these products are more toxic than the parent compounds. Mineral surfaces had limited effect on phototransformation of D9, NTO, and NQ, and particle wetting did not influence their phototransformation, but energetic transformed slower as solids than in solution. For IMs, about half of particle mass loss was due to phototransformation, and greater loss due to phototransformation was observed for TNT and RDX than in sensitive munition constituents. However, quantum yields determined in the lab overestimated field rates because light only reached thin surface layer of the particle. Batch adsorption studies with soil and soil components indicated that important roles that phyllosilicate clays play in D9 adsorption to soils. The project produced data and developed relationships needed to predict the long-term potential of traditional insensitive munitions to contaminate soil, groundwater, and surface waters.